now we're going on to the math content. First, I just want to do one quick problem of reviewing derivatives. I've made it a doozy here so that we can make sure we review a lot of the different rules. All right, so we've got f of x is the fifth root of sine of x times e to the 5 cosine of x divided by ln of x. And we're supposed to find the derivative. So when you're trying to find a derivative, you want to ask yourself, what is the most outside thing going on? And in this case, the most outside thing going on is the fifth root. So we're going to write the fifth root as to the 1/5 power. And then we're going to use the power rule to take care of that. That's our outsidemost function. So using the chain rule, we're going to get 1/5 something to the 1/5 minus 1, which is negative 4/5. And then what goes inside of that empty spot? Well, it should be whatever was inside of your outside function before, your inside function unchanged. So it's going to be sine of x to the 5 cosine of x, not x times e to the 5 cosine of x, divided by ln of x. And then the chain rule says you take the derivative of the outside function, plug the inside function in unchanged, and then you follow that with the derivative of the inside function. So we're going to need to take the derivative of sine of x e to the 5 cosine of x divided by ln of x out here. So we copy everything at the top. I'm doing this in steps just to kind of help refresh your memory. And now what's the most outside thing going on? In our new derivative, it's the sine. So the derivative of sine is cosine. And we copy all this inside stuff again without changing it. So we have x e to the 5 cosine of x divided by ln of x again. And then after that, we're going to need to have the derivative of this fraction. Okay, so how do you take the derivative of a fraction? Well, you have to use the quotient rule, right? So we're going to copy all this stuff again. There we go. I know, that's cheating. And now we're going to use the quotient rule. So the quotient rule says that we need the derivative of the top. So right now I'm just going to write the derivative of x e to the 5 cosine of x times the bottom, which is ln of x, minus the top times the derivative of the bottom. Now the derivative of ln of x is 1 over x, all divided by the bottom squared. So that's ln of x squared. So we'll be done with this problem as soon as we take the derivative of x e to the 5 cosine of x. And to do that, we're going to need the product rule. Okay. So, product rule. All right, let's copy everything again. And now where we have the x e to the cosine of x, let's make some room and use the product rule. So the product rule says we take the derivative of the first term, that's x, so that's 1, times the second term unchanged, plus the first term unchanged times the derivative of the second. So now we have e to the 5 cosine of x. This is our last chain rule. Our outside function is e to the something. The derivative of e to the something is just e to that something times the derivative of the inside. So the derivative of 5 cosine of x is negative 5 sine of x. And there we go. We've taken that horribly complicated derivative, and this whole thing is our answer. So if you followed all that, That means you're in good shape remembering your derivatives. If you didn't, you really, really need to go back and study that, because you're going to need to be able to take derivatives in your sleep without thought to be successful in this class. Okay. Now, our topic for today is undoing the derivative, also called antiderivatives. Now, if you took 151 here on the Columbus campus, you probably have already seen this topic. Briefly, there's a little bit more in the Briggs book in this section than there is in the Stewart book. So we want to make sure we talk about that. And we want to just kind of refresh all this, because this is going to be one of our main ideas for this course, is talking about antiderivatives. It's really the main idea for the entire 152 course that we're going to be doing about half of in our current class. Okay, so undoing the derivative. So this is if they give you questions like, you know f prime is 2x, what's f? Well, think to yourself, what function has a derivative of 2x? What is it? Well, x squared. That's probably what you're thinking about, right? And the derivative of x squared is 2x. That's fabulous. But is that the only one? Could you think of another function who also has a derivative of 2x? What if I said f of x was x squared plus 3? What would that derivative be? It would be 2x plus 0. So it's still 2x, right? What if I said f of x was x squared plus pi? Or f of x was x squared minus the square root of 182. All those things have a derivative of 2x. So what can you tell me in general? In general, f of x is going to be x squared plus some number, some constant that we don't know what it is. And that's called the general antiderivative of 2x. Okay, so when we're thinking about antiderivatives, we're actually getting a family of answers. It's all the functions that are vertical shifts. So this line, if you shift it up and down, all of those are solutions to where the derivative is 1, and then the antiderivative is x plus a constant. Over here, if g of x, this black curve, is one of the solutions, then any other vertical shift of that is also going to be a solution. And this is an example of what we call an interactive figure, and these are embedded in your textbook. So as you're reading your textbook, you can play with these, and they'll really help you develop more of a conceptual understanding of what's going on. So I really encourage you to do that. You'll also sometimes have homework questions where you're asked to play with one of these to come up with an answer. All right, so here's another problem that you might see. What if the second derivative is 2x? What can you say then? Well, it seems pretty obvious then that the first derivative is the antiderivative of the second derivative. That must be x squared plus some constant. But they actually give us some extra information. They tell us that at 0, the first derivative has to be 0. So if we plug that information into our function, we'll get g prime of 0 has to be 0 squared plus c, but it also has to be 0. So that tells us c is 0. Okay, so that tells us that g prime of x is just x squared. There's no other constant that goes with it. And so if g prime of x is equal to x squared, then g must be, well, what function, when you take its derivative, do you get x squared? So usually when I ask that, people say that they're thinking about x cubed. But when they take the derivative of x cubed, they get 3x squared. So how are we going to deal with this extra 3? Well, what if we took our original function and we put a 1/3 in front of it? So if we said the antiderivative was 1/3 x cubed, then when we took the derivative of that, we get 1/3 times 3 x squared, which would be just x squared, which is what we want, right? So our antiderivative is 1/3 x cubed. We've added 1 to the 2, and then we've also divided by that same number. And then, of course, we need to add another constant. Let's call it k this time so we don't get confused with the c we had before. So those are all the possible functions that could be g, given the conditions we started with. But how do we know we got all of them? How do we know there might not be some other function that we didn't find that also has a derivative, the second derivative being 2x? Well, the reason we know is because of this theorem. This is theorem 4.16 in your book. And it says that if you have one of the antiderivatives, then all the other antiderivatives have to be just a constant away. You can't have two completely different functions having the same derivative. Okay, so antiderivatives. First of all, this is the notation for antiderivatives. This is called an integral sign. And then you have your function here, and then the dx. So both the integral sign and the dx are part of the antiderivative notation. And whatever's in the middle here, this is the thing you're trying to find the antiderivative of. And we often say that one antiderivative of little f is capital F, and then we add c to that to show that we have a whole family there shifting up and down. Okay, so here's a bunch of things that we should know they're antiderivatives. If you have a constant times a function, then when you find the antiderivative, it's just a constant times the antiderivative of the original function. If you're adding two functions together, then you can take their antiderivatives separately and then add the answers. If you have x to the n, then we just said you add 1 to n and then divide by that same number. If you have 1 over x, what function's derivative is 1 over x? Well, it'd be natural log, right? Derivative of natural log of x is 1 over x. But there's a little bit of a problem, because I can plug any number but 0 into 1 over x, right? Everything but 0. But in the natural log, I can only put things bigger than 0. So how do I deal with the negative numbers? Well, it turns out that if I take a natural log of the absolute value, then that's going to fix my problem. The antiderivative of e to the x is e to the x. What function, when you take its derivative, do you get cosine? Well, the derivative of sine is cosine. What function, when you take its derivative, do you get sine? Well, you might think it's cosine. But remember, if you take the derivative of cosine, you actually get negative sine. So to take that negative into account, we have to put a negative out front. So the antiderivative of sine is negative cosine. The antiderivative of secant squared is tangent, because the derivative of tangent is secant squared. Similarly, the antiderivative of secant tangent is secant. The derivative of secant is secant tangent. Now, these last two you might not recognize, but these are examples of some of the inverse trig functions derivatives that you've seen before. So if you take the derivative of inverse sine of x, you actually get 1 over square root of 1 minus x squared. And if you take the derivative of inverse tangent of x, you actually get 1 over 1 plus x squared. Now, there's a chart of a lot more of these in your book. So make sure you look there at all of the functions that you're supposed to have their antiderivatives memorized for. All right, so here's an example of a problem you might see. Antiderivative, if you know the derivative is 4 sine of x plus 2x to the 5th minus square root of x divided by x. How do you find the antiderivative of that? Well, the plus sign means we can focus on each of these separately. The 4 out front means it's just a constant. We can ignore it, so we just bring it down. The antiderivative of sine, we just said, was negative cosine. But then how do we deal with this fraction here? We didn't say anything about taking antiderivatives of fractions. And as a rule, it's really hard to take an antiderivative of a fraction or of things being multiplied. So we need to find a way to simplify this before we take the antiderivative. So we're going to rewrite this as 4 sine of x plus 2x to the 5th over x minus square root of x over x, which is really just, this is 2x to the 4th, and this is square root of x divided by x, so that's, we're thinking x to the 1/2 over x. And remember, if you're dividing, you subtract exponents. So we're actually going to end up with x to the negative 1/2 over here. Okay, so now we get to take the antiderivative using the power rule. So we're going to just bring that 2 along, and then x to the 4th becomes x to the 5th, bump the power up by 1, divided by 5. And x to the negative 1/2 becomes x to the 1/2, bump the power up by 1, divided by 1/2. And then at the end, we put that plus c, because we don't know if there was a constant or not. Here's another example. This time they give us a point. So the difference with this example is we're going to not have that plus c when we're done. We're going to have an actual number instead. We're going to be able to find the particular antiderivative that they're talking about. So first, we have separated by addition the e to the x and the 20 times 1 plus x squared. The antiderivative of e to the x is e to the x. Plus, and we have 20 times a function, so we can ignore the 20. And then the antiderivative of 1 plus x squared, the antiderivative of 1 is x. And the antiderivative of x squared is x cubed over 3. Bump up the power by 1 and divide by it. Now we are going to put the plus c here, but we're not done, because we need to figure out what c is going to be the actual solution to this problem. So we're going to plug in the point they give us, f of 0, which would be e to the 0 plus 20 times 0 plus 0 cubed over 3 plus c is supposed to give us negative 2. So e to the 0, that's 1, plus 20 times 0, that's 0, equals, plus c, right? Plus c equals negative 2. That means c must have been negative 3. And so going back and plugging into our equation that we found for the antiderivative, we find that f of x is e to the x plus 20 times x plus x cubed over 3 minus 3. And there's our answer. Okay, so now we want to talk about, this is the part that's new that you may not have seen before, finding antiderivatives of f of a times x, where a is some constant. All right, so what if we want to define something like the antiderivative of cosine of 8x? So we might think that that might be sine of 8x. What do we think? It might be sine of 8x. We could check that. We could check and see if we're right by taking the derivative of sine of 8x. So if we took the derivative of sine of 8x, we'd get cosine of 8x. That looks good. Times 8 from the chain rule. Right? We take the derivative from sine of 8x to cosine of 8x. We get cosine of 8x times 8. Okay. So how do we fix that? If we wanted our derivative to actually just give us cosine, well, we can fix it by putting a 1/8 in front of the sine of 8x. That'll put a 1/8 in front of the cosine of 8x times 8, and it'll make the 8 and the 1/8 cancel, and we'll have that derivative that we want. So, what's that telling us? That's telling us that capital F of x must be 1/8 times sine of 8x. And then plus c, because we always have to put a plus c. So what was the pattern there? If you have any function where you have plugged in a number times x, the way we just had 8 times x, when you take its derivative, you're going to get the derivative of that function with the ax plugged in it times a from the chain rule. So if we're trying to find the antiderivative to compensate for that chain rule, we're going to have to put a 1 over a out front of f prime of ax. So there's your formula. Anytime you have a number times x plugged into a function, oops, no prime there. Anytime you have a number times x plugged into a function, and you're trying to take the antiderivative, you have to put 1 over that number times the antiderivative of your function. All right, so let's try that. If you have e to the 5x, then the antiderivative of that is going to be e to the 5x again, because the antiderivative of e to the something is e to the something. But we have to compensate for that 5, so we put a 1/5 out front. And then we put a plus c. Does that make sense? Now we also have problems like 1 over 9 plus x squared that don't exactly look like they're in that format, but they will be with a little bit of manipulation. So we could rewrite 1 over 9 plus x squared. We're trying to make it look like 1 over 1 plus something squared, because we know how to take the antiderivative of 1 over 1 plus, I guess if we want ax squared. We would know how to take the antiderivative of that, right? The antiderivative of that is supposed to be arctan, or tangent inverse, of ax. And then we have to put a 1 over a out front to compensate for the a inside. So how do we rewrite 1 over 9 plus x squared to look like 1 over 1 plus ax squared? Well, we need to turn this 9 into a 1. So we're going to pull a 9 out of the bottom. We're going to get 1 over 9 times 1 plus, and that leaves us with a 1/9 x squared dx, which we can pull the 1/9 out front because it's just a constant. Then we're going to have 1 over 1 plus, and now we needed ax, the whole thing squared. So how can we rewrite 1/9 x squared? We can write it as 1/3 x, the whole thing squared, dx. And now applying this formula, the antiderivative is 1 over, here a is 1/3, right? So 1 over 1/3 arctan of 1/3 x plus c.
All right, and to finish this problem, we need to take this 1/9 that was out front of this integral and put it out front of our antiderivative. So that gives us, this is a 3 here, that gives us 1/9 times 3, that gives us a 1/3 arctan of x over 3 plus c is our final answer. And please note that in your book, in the antiderivative section, they give you antiderivative formulas for a bunch of functions where instead of an x, they have an ax. And you need to know how to do those. You need to make sure you have all those memorized. So for example, integral of sine of ax, things like that. That is new. That was not in the Stewart book in the antiderivative section.
So one of the big applications of derivatives was with position and velocity and acceleration. So that's a big application of antiderivatives as well. If you're given the acceleration, like here you're given the acceleration is 6t plus 4, then we're asked to find the position function. And they're given the initial velocity and the initial displacement. So the acceleration function, remember that's the second derivative of position. So that's s double prime. And if we want to get to s, we need to take antiderivatives. So we take the antiderivative of s double prime, we get s prime, which is also the same as v. And that's going to be 6 times t squared over 2 plus 4 times t plus a constant, which simplifies into 3t squared plus 4t plus a constant. Now we need to use the fact that the velocity at 0 is -6 to figure out what that constant should be. So velocity of 0 equals 3 squared plus 4 times 0 plus c, and that's supposed to equal -6. So 0 plus c equals -6, so c equals -6. And plugging that in, that gives us that our velocity function was really 3t squared plus 4t minus 6. Okay, so then if we want to go from velocity to position, remember that velocity is the derivative of position. So we're going to take one more antiderivative, and we're going to get position is 3 times t squared, t cubed over 3, plus 4 times t squared over 2, minus 6t plus c. Now this is a different c, so let's call it, let's put a hat on it, c hat. That way we don't get them confused. And how do we find c hat? That's the last thing we need to do, and that we use the information that the original displacement, the original position, is 9. So s of 0 should be, well, we can cancel these 3's, right? 0 cubed plus 2 times 0 squared minus 6 times 0 plus c with a hat on it is equal to 9. That tells us that 0 plus c with a hat on it was 9, so c with a hat on it is 9. So our final answer here, s of t, the original position function, was t cubed plus 2t squared minus 6t plus 9. So there's one application of using antiderivatives. And that is the end of our first lesson. Thank you very much.